Hello everyone, we are Group B. Our topic is femtosecond pulse generation by nonlinear optical gain modulation. Here is the outline. We will divide it into 4 parts. They are the introduction, concept and experiment, numerical simulation, and the conclusion and discussion. The first part is the introduction. We'll introduce the ultra laser generation background and what is the nonlinear optical gain modulation. Ultrafast laser plays a crucial role in modern scientific research and industrial application. However, generating the high-quality ultra-short laser use a simple and versatile method remains a challenge. Molar lasers are traditional and highly effective for ultrafast pulse generation, offering an extremely low noise and high coherence. But instead, they require complex cavity design to stabilize the pulses. High-Q microresonator enable compact integration for industrial and the formation of dissipation curved silicons and microcombs. However, they typically need milliwatt level pump power and face the limitation in output pulse energy. EO modulation offers a flexible repetition rate and high coherence, but it shares a less efficiency due to the modulator. And gain switch diode or JSDS provides a simple novel approach for arbitrary repetition rate, but they still requires external pulse shaping to reach a femtosecond scale and still suffer low overall efficiency. These challenges highlight the need for a new approach that combines high performance with a simple, compact configuration. This set the stage for the introduction of the nonlinear optical gain modulation. NOGM is a technique to transform a continuous wave laser into femtosecond scale pulses using a simple setup with a Raman fiber amplifier. It uses the property of a high coherence of the CW laser and nonlinear gain shaping from picosecond pump pulses to achieve the modulation of a optical gain to reshape the CW light into ultrafast pulses. In this paper, they earned a 436 femtosecond in the end. NOGM has a clear advantage. It features a simple structure, flexible wavelength tuning, high conversion efficiency, and high coherence. This method will open a new possibility for ultrafast laser applications. Now, let's look at how can they do this and how their results. So, in the second part, we will introduce the NOGM scheme, the experimental setup, and the result. This idea is based on modulating the gain of a CW laser without using electronic or low-space modulator. Here show how it works. First, start with a single frequency CW laser, which by itself emitting a steady light wave. Second, the CW laser passes through a Raman fiber amplifier, where the gain medium is an optical fiber. Third, the amplifier is pumped by the pulsed laser. So due to the stimulated Raman scattering, a fast nonlinear effect in Sika fiber. This short pump pulse will create an equally fast time varying gain for the CW laser. So essentially, the CW laser experiments a burst of the gain from the shape of the pump pulses to reshape it into short pulses in time domain. In the frequency domain, the modulation turns the single frequency of the CW laser into a frequency comb with spacing determined by the repetition rate of the pump pulses. Here's how they put the theory to the test. The parameters are listed in the picture for your reference. The important thing is that they use two types of fibers were tested for the fiber amplifier. OFS Raman fiber has higher gain efficiency but higher splice loss as well. PM980 fiber has lower gain but better fiber matching and lower loss. The pump and seed are combined using a polarization maintained WDM. And sent through the Raman fiber. After fiber, the output is separated, compressed, and measured. Here, they use a grating pair as a compressor. There will be three nonlinear effects dominate in different time duration. The figure on the left shows the energy diagram of stimulated Raman scattering. The figure on the right shows the energy diagram of second-order Raman scattering, which will happen when the stock wave is strong enough. It can act as a new pump to generate light at an even longer wavelength. The third one is four-way mixing process. It will happen only when the phase matching condition is allowed. The two stock waves and the pump wave will generate a new frequency at 1180 nanometer. It should notice that also the newly generated frequency is the same as the second order Raman scattering. The mechanisms are different. This figure shows the initial parameters of this experiment. B shows a spectrum with a central frequency at 1064 nanometer. C shows the temporal shape within a pulse width of 14 picosecond. And figure D demonstrates the single frequency seed laser spectrum. First, we want to present how the output spectrum broadens with pump power increase. Here they use OFS Raman fiber to demonstrate it. There are a few points we can observe carefully from this figure. First, at a low pump power, a pedestal appears around the CW seed. Second, with higher pump power, this grows into a broad spectrum central at 1121 nanometer. Third, at around 1180 nanometer, a new peak appears when the input energy is large enough. These points are caused by the two mechanisms we mentioned before, and the following numerical simulation we will give a deeper introduction. Remember that we have two types of fiber, so here we do a comparison with them. Figure A compare the output spectrum, and you can easily find that the conversion efficiency are similar due to the fiber length, but the second order stock light is changed. Figure B shows the power versus pump power curve and indicates the efficient conversion and the threshold pump power difference. The optical efficiency at around 1 watt input is around 69.4%. Figure E and F are the autocorrection trace of the output pulse before and after compression in two fiber. In OFS fiber, the pulses can be compressed to 436 femtoseconds experimentally. The third part, we will discuss the simulation to explain the process of amplification and the difference in two fibers. They use a nonlinear Schrödinger equation to simulate how the input pump pulse convert into a Stokes wave pulse. We first examine the result of the OFS Raman fiber, which has higher Raman efficiency. The graph in the right row shows the spectral evolution as the light passes through the fiber. The second and the third rows shows how the pump and output pulses change as they propagate through the fiber. Now, we look at the result at the short propagation distance at 0.4 meter. Most of the energy remains in the 1064 nanometer pump pulse, and a portion is converted into a 1121 nanometer Stokes wave. In the time domain, you can observe that the pump pulse decrease while a new Stokes wave pulse begins to form. But there is still a small portion of the 1180 nanometer wave generated. This is caused by the four-way missing process. As the distance increases, most of the energy goes to a Stokes pulse because the pump is already depleted. The 1180 nanometer wave doesn't appear. As the propagation distance increases further, the strong Stokes wave undergoes second-order Raman scattering, converting 1121 nanometer to 1180 nanometer. This is the final result after 2 meters. We can observe that due to the onset of the second-order Raman scattering, the Stokes wave becomes depleted. Now, let's move on to the PM90 fiber simulation. At 2.5 meters, we can see that the 1121 nanometer Stokes wave continues to grow, but the 1180 nanometer component is still very weak. As we further increase the fiber length to 4, 6, and even 8 meters, the Stokes waves gradually become stronger, but no second-order Raman scattering is observed in this case. This is because that the Raman gain efficiency of the PM90 fiber is much lower, so a longer distance is required to reach the same level of the nonlinear interaction. It should be noticed that due to the walk-off effect between the pump and Stokes pulses, the pulse shape become asymmetry, and the temporal phase also become more nonlinear, which make it harder to compress the output pulse properly. This explains why the compressed pulse from PM90 fiber has a broadened width but cannot be compressed perfectly. This figure can more clearly demonstrate the multi-Stokes line effect. We can see the pump pulse energy rapidly decrease about 0.3 meters and induce efficient and transform to first-order Stokes line. It also happened at around 1.8 meter in the PM fiber. After 1.5 meters, the second-order Stokes line began to grow. This is a clear sign of a second-order Raman scattering. Eventually, as the second-order process becomes dominant, the first-order Stokes wave starts to decrease. However, it didn't happen in PM90 fiber due to the lower Raman gain efficiency and walk-off effect. Due to the generation of higher order Stokes component is no use in an OGM. This result confirms that proper Raman efficiency and walk-off effect can suppress the second-order Stokes line. From result and aspect mentioned above, they simulate a better situation with high pump pulse energy and shorter length of the PM90 fiber to generate optimized output pulses. Figure A, B, and C shows the output spectrum, the temporal pulses before and after gradient compression. It can finally achieve 188 femtosecond pulse width. However, the instantaneous frequency still shows some nonlinearity, indicate lasting residual chirp. The last part is our conclusion and some discussion about extension. In this report, we show the principle of the nonlinear optical gain modulation and presents a simple structure to generate a high-efficiency femtosecond scale output pulse with a 30 times pulse width reduction. Moreover, we can compare 2 times of Raman gain fiber in experimental data and theoretical simulation. The four-missing multi-order Stokes-Light walk-off effect are observed and deeply result in the final output pulses. We also demonstrate the potential and ability of the NOGM with the optimized pulse situation by tuning pump pulse energy, fiber length, and so on. However, there are challenges. The use of longer Raman fiber will introduce a pulse walk-off and nonlinear chirp, which limits the compression performance. In our future research, we should focus on optimized fiber length and pump energy to minimize this effect. For future potential of the NOGM techniques, here are listed 2 potential works. First, by multiple stages of nonlinear optical gain modulation, we can achieve higher order Stokes generation on purpose to effectively extend the wavelength range. This means that our system could generate light in multiple distinct wavelengths. Why is this important? In applications like multiphoton fluorescence microscopy, different wavelengths can selectively excite different fluorescent molecules, enabling detailed biology imaging. In spectroscopy, extending wavelength range broadens the types of material and chemical bonds we can analyze. And in optical communication, it supports multi-channel high-capacity system by providing multi-wavelength channels for data transformation. The second work is the development of a stabilized frequency comb system based on this setup. Traditionally, stabilizing a frequency comb requires a complex system to measure and control a carrier envelope offset frequency. But with the NOGM, we use a single frequency seed laser whose frequency is inherently stable. This means that FCO is directly determined by the seed, which eliminates the need of the compressed reference unit. This simplified structure enables potential applications like optical frequency metrology and atomic clocks, where precise and stable frequency reference are essential. These 2 examples highlight the flexibility and future potential of this technique. They open the door to advanced application in modern scientific research, but not only the ultrafast pulse generation. Thanks for your listening. Well, goodbye.